the story of how it comes to be. Hello, I'm Brian Unger.
I'm Professor Lou Bloomfield.
From the drawing board to the assembly line, it's how the ordinary is actually extraordinary. Today on Some Assembly Required, bowling balls, jelly beans, and toilets. If you think the bowling ball is just a glorified marble, then think again. From the core to the finger holes, everything about this ball is engineered to improve your odds of bowling a strike every time. How is a bowling ball designed to help you have the game of your life? We're at Ebonite, a world leader in bowling balls, to find out.
I'm here with Jennifer and Laretha. We're at the very, very head of this assembly for bowling balls at Ebonite in Hopkinsville, Kentucky, folks. And this is essentially where we find the nucleus of the ball, where that gets formed. And all these sort of mixtures of resins, these plastics, are all brought together to this tube. Now I'm just gonna fill this mold here with the resin that becomes the core, and eventually they're gonna get baked and hardened.
Once solidified, this resin becomes the center or core of the ball. Yeah, this is the core. There are nearly 24 core shapes in the Ebonite stockroom, and it's the shape of each one that defines how the ball's gonna roll.
Hey, Billy, can I have one of those cores? So, this is the beginning of the ball. Let me ask the obvious question. Why is it not perfectly round?
Well, to answer that question, we first got to look at the idea of mass.
Even though the bowling ball is classified by weight, the real issue isn't how gravity pulls on it, but how hard it is to shake and twist as it goes down the lane. Some balls, like house balls, have a perfectly round core inside and therefore a perfectly symmetrical axis. Those balls roll exactly as you'd expect every time. But balls with asymmetrical cores twist more readily in one direction than another. So these balls don't roll down the lane, they actually wobble.
It gives it essentially power steering.
So you're creating an imbalance. An imperfect ball allows the player more control.
Right, it's a perfectly imperfect ball.
To take advantage of this power steering, it's crucial to know how that core is positioned inside the ball and which way it will ultimately spin.
Ah, a fresh basket of cores.
A core twists along 3 axes, X, Y, and Z. The X and Y axes dictate the all-important wobble, so they're measured and marked.
We're ready to move on. Hey, where do they put the finger holes in this?
Then the axes are drilled.
Oh, right in there, yep. I'm just gonna suction some of this resin as it's coming off here.
2 holes, a big one and a small one.
And voila, we have the hole. Very important. Now, eventually, this little doodad will be positioned inside this hole.
This pen will stay in place throughout the entire process, layer after layer, from core to veneer, pointing to this hole. But what exactly is it pointing out?
All right, gentlemen. Lou and I are with Ron Hickman, who's the chief engineer here at Ebonite. I've drilled this hole, and I essentially know that it's going to tell the pro shop eventually where this core is inside the ball. But why drill it here? Why not drill it over here or over here?
Things you drilled are identifying the principal axes of this core. This is the hardest axis about which to twist the board. This is the easiest one, the big hole.
The pro shop needs to know where these 2 points are located so that they can best orient your finger holes for control over that wobble.
Really what's going on here is the orientation of these holes is going to allow you ball motion or type of hook. And the more hook you have, the more entry angle you can achieve. The more entry angle you can achieve, the likelier you are to get a strike.
So essentially, it's an X on the map to the guy who drills the finger holes, telling him or her how to get the most out of your ball.
Exactly.
So what happens next?
So now that we've crafted our core, it's time to turn this odd-looking shape into a ball. And for that, we mark our holes, center the core into a second spherical mold, and fill it in to form the outer core.
This is my favorite part at Ebonite. Paper clips. Hold that together.
Sounds easy, right? Not quite. Every ball has to be 27 inches in circumference, but it can weigh anywhere between 6 and 16 pounds. So, how do you make same-size balls with such varying weights? Well, it all comes down to tiny bubbles.
So Ebonite's task next is to create a spherical object without undoing all the engineering of that core. Well, to do that, they wrap the inner core, the core we've been dealing with, in an outer core that is a much lower density.
Ebonite uses filler made of tiny glass microbubbles. They're like mini Christmas ornaments, as light as styrofoam, but extremely durable and tough. To get the balls to the right weight, they mix these glass bubbles with another denser filler. Varying the proportion of these two fillers changes the ball's weight without changing its size. To get the most out of the ball's power steering, it's critical not only where you place the core, but how it's centered.
We can't have that sticking out. How's that? Okay?
Too short.
Too short?
Cut too short.
I cut it too short.
He's trying to center the mass, but he's also trying to orient it exactly right.
Well, ultimately what happens when you have the proper orientation, you're going to create what's called a top weight. The top weight is used by the pro shop to know exactly how deep to drill the finger holes so that when it's all said and done, you can get the ball balanced the way you want it to be.
As the resin dries inside the mold, our creations are actually starting to look like bowling balls.
Well, I'm here with Brian Hickey, who's the Director of Operations here at Ebonite. And what we have here is our mold. We poured our resin filler in here. Now, Brian, how do I get this thing apart?
Crack it like an egg.
Crack it like an egg, really?
The introduction of the asymmetrical core in the 90s gave bowling a big popularity boost. It was easier to bowl a strike, so more and more people came out to play. Now some 70 million Americans hit the lanes every year. So to keep up with the growing sport, Ebonite makes up to 5,000 balls a day. It's a lot of balls.
Once again, Discovery slowing up production in American industry.
At the Ebonite factory in Kentucky, our bowling balls have the power steering core. Now we need some traction, so we put the ball into a third mold and pour in some plastic. This is no ordinary plastic coating. It's chemically constructed to give the ball a firm grip on the lane, allowing the bowler even more control.
Hey, Alicia, give the professor a drink.
Look at that. It looks like red wine here, right?
Oh, it looks like blood.
When she served it up to me, it consisted of polyol molecules and isocyanate molecules. And they are now reacting with one another like crazy in there. As the molecules grow, it becomes more and more viscous until finally it's so viscous that if I begin pouring it, it should harden right before our eyes.
Oh, cool. Can I touch that?
You can touch it. It's already gelled.
The other cool thing, which you can't see, is the third material in here, the plasticizer. At this temperature, the plasticizer starts evaporating, leaving microscopic holes in the ball's surface.
These holes will soak up some of the oil that coats the lane and create traction. Traction allows the ball to change rotation onto its preferred axis and hook so that it hits the pins from the side. This side area, known as the pocket, is key because it gives the best angle for strike after strike after strike. It only takes 2 minutes for the polyurethane coating to harden on the ball's surface, but it's still got a lot more baking to do.
The plastic, that urethane outer shell, is still forming. The chemicals are still reacting, and this ball continues to get harder and harder.
In the oven, the veneer cooks and the plasticizer continues evaporating to achieve the right porosity. In this case, the more porous it is, the better the performance. The balls pass from the piping hot oven right into the fridge.
That feels real nice.
This cools the plastic down so we can finish making our balls. The exposed pin heads are now the markings that the pro shop will look for when they drill the finger holes.
The only way to prove that this ball has the high performance we claim, the power steering, is to test it.
If the ball is made correctly, the spin will eventually rotate the ball onto its preferred axis, marked still by the pinhead, and this etched sign.
Ready? Get set. Go. Look what's over here now. It loves that axis. That's the power steering. This ball turns its rotation to spin about that pin.
We got power steering, we got traction, now we need some speed. That's where polishing comes in. This process gives the ball its tread, helping it slice through the lane's oily finish and speed toward the pins. The result, incredible striking power. To polish the ball, we first smooth over any rough patches. This grinder shaves 1/10 of an inch off the circumference in just 30 seconds. The balls are weighed one last time and then showered in polish. The oil conditions of the lane will then determine the amount of polish you want. If the ball's too glossy, it will hydroplane on a heavily oiled lane. This ball may look finished, but there's one more step.
We'll get your hole size, and then we'll go right back there and start drilling holes. Don't make bowling harder than it is.
I like the way you think, Roger.
All the calculating and engineering, the physics and chemistry, it all comes down to this final stop on the assembly line, the pro shop, where they can literally make or break a bowler's game.
Huh?
Reach around my arm right there and let's see how you do it.
You ready?
Yeah, I'm ready.
Now, you want me to grab your wrist?
The pro shop measures our fingers and the span of our grip, then uses the two axes still clearly marked to map out the holes.
I'm ready.
Y'all ready, huh?
Let's go, Raj.
Then he drills. Now, if they're off on their measurements, even the highest performing ball thrown by the most expert bowler will miss its mark. Every model of every Ebonite ball goes down these lanes to answer the very critical question: will this ball do what it's designed to do?
This is kind of really where the rubber meets the road.
So how do these guys measure and analyze their balls? They use telemetry.
What we have is a tracking system here, and what it does is it uses video to actually record the ball going down the lane.
Recorded and analyzed against the expectations of that particular ball.
As the ball goes down the lane, collects the information as to where the ball is on the lane, and then what you can actually see is the ball path that the ball took. It allows us to see exactly how the core relates to the coverage, relates to the ball, relates to the lane condition as the bowler is actually using it.
Oh, cool. My custom-made bowling ball has the right telemetry.
Where's the thumb hole?
But will it help get my game out of the gutter? Because it's bad.
When I'm down here, I still got the ball. So when I get ready to come through here, thumb comes out, follow through with the fingers.
You just open up a whole new
Follow through
world
with the fingers, and then you're able to guide it.
Wow.
I'm learning here that the right ball still won't strike if it's in the wrong hands. But with some really good coaching, it all starts coming together.
Jerk.
Yeah.
You're going to do all this
Yeah.
stuff. It's got to
pitch it
be
right into the
clean,
gutter.
come out of
Okay.
it first.
All right.
And eventually, well, it's not a perfect game. But I am very proud.
And I'm going to enjoy this moment because it's the last time it's ever going to happen.
This could be the most highly engineered product on the face of the planet.
Fairfield, California is home to the world-renowned Jelly Belly. What makes a Jelly Belly more than an ordinary jelly bean are gourmet flavors that amazingly taste just like the real thing. So, how do they pack so much flavor into this? Pina colada, strawberry, whatever your taste, it all starts with a simple test.
At Jelly Belly, the first step in composing a flavor is pretty low-tech. Humans and their taste buds and noses sample various flavors and pick the one they like. This is what you might call molecular gastronomy. Every flavor you've ever tasted tastes that way because of specific molecules it contains. Lemons, they smell like lemons largely because of a molecule called limonene, and they taste tart because of 3 other molecules, citric acid and vitamins A and C. Pear starts with butyl acetate, cotton candy with methylphenol, and coconut with gamma-octolactone.
Once the staff settles on the flavor of choice, then the process moves on to a gas chromatograph. It analyzes the flavor's chemical composition and generates a recipe. These ingredients form the recipes that eventually produce Jelly Bellies in the billions. So, who's the man behind the bean? His name is Herm Roland.
Herm, you're CEO of Jelly Bellies.
Yeah.
You're a force of nature. When you walk in the room, you can just feel your energy. Do you ever walk in here and just say, make me banana cream pie and I want it by the end of the week?
No.
No?
I wouldn't do that.
But you have how many flavors?
Well, there's 50 official, but we probably make 100 altogether with all the different seasonal flavors.
They even make a few flavors that are, well, disgusting.
You don't really eat this, do you?
Oh, sure, eat it. It's good. It's right on. Isn't it right on?
Vomit.
Oh! It's okay to spit.
Yeah, vomit. A flavor based on the Harry Potter craze is, believe it or not, a top seller. Now, if that's not gross enough for you, how about earwax?
Normally, you'll go to a flavor company and say, get me earwax. Well, earwax, what's that taste like? Well, everybody's earwax tastes different, right? So I let my ears go for a couple of weeks. And then I dug them out and mixed it up and tasted it.
From this lab, and yeah, even the boss's ears, comes Jelly Belly flavors turned confections. At the heart of every Jelly Belly is 4 ingredients: water, corn syrup, corn starch, and sugar.
This is where it starts.
This is.
In
our kitchen.
the kitchen?
Yes, it is.
It comes from this sort of big heated cauldron of what do you
Corn
call it?
syrup.
Corn syrup.
Sugar. Starch. Water. It's a slurry.
A slurry, of course. And then you pump it through these pipes and down in here.
That's correct.
Oh, here it comes. Check this out. It's starting to fill up with, kind of looks like turkey gravy.
This is the first ingredient I add to the slurry. It's a highly concentrated flavor we generated back in the lab.
This amount of flavor and this amount of color will color and flavor over 400 pounds of bean centers.
This is enough for 400 pounds of Jelly Belly beans?
That's correct.
Just that much?
Just that much.
This is kind of like a nuclear bomb of cherry, isn't it?
It's getting there.
And then this is enough color for the same 400 pounds of beans?
That's correct.
All right, so in we go.
Try to hit the vortex.
Wow, that thing goes red pretty fast.
We'll fire off the switch and let it head down to be deposited in our mobile.
So we're gonna send this downstairs?
Yes, we are.
All these kitchen cauldrons need to be synchronized, so as our slurry level drops, a sensor alerts a central computer. Then part of our mix goes to storage for cooling, and that's going to be used later in the process.
This is where you can see the Jelly Belly bean taking shape for the first time. It is injected into these molds made of cornstarch.
So why do they use cornstarch? Well, it's porous, and that soaks up moisture to help speed up the drying. Here, everything moves fast. These injectors here spit out bean centers at the rate of more than 35,000 a minute. There are 2 of these machines cranking out more than 4 million beans an hour.
You look mesmerized, Lou. Kind of like watching the ocean. Here's my question for you, Captain. The bean is rounded on the top and it's rounded on the sides. Now, why doesn't gravity just flatten the bean and push it down like a pancake?
Because of surface tension.
The surface of any liquid acts like an elastic membrane. When gravity tries to flatten the bean's surface stretches, and surface tension fights back, rounding the top of the bean, like this water balloon.
Rounded just right, the Jelly Bellies are poured down a conveyor belt, sent through a steam oven, like a Jelly Belly sauna. It heats them up to 80 degrees and prepares them for the next step. Take a look at this. This is the center of a Jelly Belly bean, and right now it is more jelly than bean. As compared to this, the finished product of the same flavor. It's about 40% bigger, just like you or me. You add a little sugar, and you get fatter.
2 scoops. And shake it on there. Yeah.
In this process called engrossing, they add 4 layers of sugar. That's going to make our bean 40% bigger.
Oh, look at that. Loads and loads of carbohydrate goodness.
Now come down to the other end.
This whole process is done by hand. There are no machines tracking the color or the amounts of sugar. It's just a bean maker and his beans.
Now this candy's been running for long enough already, and the sugar's packed on the center itself.
So it's time to add another layer of sugar.
Yes.
One thing they are not in short supply of here at Jelly Belly is this white stuff, sugar. They'll go through one of these big giant canisters of sugar in 20 minutes.
We're gonna have to pick up the pace a little bit.
Driving me like cattle here.
Well, once it starts running real rough, it's taking a little too long to get the sugar on there.
Okay.
I'm gonna come down here and put another scoop in real quick. I need to catch it back up to speed.
I'm pulling this thing behind. I'm slowing it down. Now watch the pro do it.
We've got to give these beans an even coat and make sure they don't stick together. That's what the movement does, but only if the sugar and syrup are added at a perfectly timed interval. Now, Barry knows by the sound of the beans that I am way behind.
This is what happens when you don't put sugar on fast enough.
Like what I was just doing?
When you're taking your time, you can't take too much time while you're making it.
We're here at the Jelly Belly factory in Fairfield, California, and we created the cores for the Jelly Belly batch, and we put them on a strict diet of pure sugar. Now it's time for a heavy dose of flavor.
Okay, so now with the candy's dry enough, so we're gonna put a wetting on it.
The wetting?
This is syrup and color.
Syrup and coloring?
Yes.
Basically looks like milk.
Ordinary jelly beans have flavoring only on the outside, not Jelly Bellies. Their intense flavor is on the inside as well as the outside, which makes them unique. Okay, more wetting, more sugar. These beans are growing fast.
So 4 times we gotta add the syrup and the coloring, and then more sugar, and so on, and so on. By adding all of that flavor, we are creating a veritable powder keg of taste. All of that flavor is encased inside this Jelly Belly bean within this soft shell of the candy. What releases it is biting into it, thus creating the Jelly Belly experience on the taste bud. That is a really pedestrian way of explaining the science of flavor. Forgive me, Lou, but what's really happening?
Most of what you think of as flavor is actually smell, not taste. I can show you this. Pinch your nose off and taste this bean I've got in my hand.
All right.
Here you go. Got it? Ready?
Yeah.
Taste it.
Yeah.
What is it?
I have no idea what that is.
Now open your nose.
Oh, coconut.
That's it, right? When a person chews, flavor is unlocked and those molecules hit the olfactory system and create nerve impulses that head to your brain and bam, you taste the flavor.
So how do you keep the flavor in one bean from jumping into the bean next to it?
They have to keep the little volatile flavor molecules inside each bean until you bite into it. Jelly Belly puts a shell around each bean to keep those flavor molecules in place. Now, out of all the processes we've done, this is the loudest in Jelly Belly. You can't hear a thing in here. What?
What?
Yeah, a little noisy in here. At this point, we're adding 10 layers of color glaze, which lock in the flavor and form the shell. This glaze is a sugary syrup. It's loaded up with color and flavor and gives our bean a nice shine. Amidst all this deafening noise, our beans are getting buffed, kind of like a rock in a rock polisher.
These Jelly Bellies are basically finished. After a coating of color and glaze has been added, they're dried in these tumblers using this blow dryer, basically.
The flavor's locked inside and we're ready to eat these beans. But first, we've got to inspect them. For the final stage of our Jelly Bellies, we filter them twice. These cylinders are like giant sieves, and only the perfectly sized Jelly Bellies get through. The ones that are too small or too big get trapped. They reject about 1,000 pounds of beans every day here, and the ones that don't measure up are packaged and sold as, what else? Belly flops. After all this, some bellies manage to make it through because they're too long or too thin or just determined.
They all look alike. Ah! That's a bad bean. This bean tried to make a break for it.
The good ones are bagged, boxed, and shipped at a rate of 100,000 pounds a day. What started out as a gooey slurry loaded with volatile flavors was molded, bathed, and smothered in layers of sweetness. Encased in a soft but tasty shell, it's now a fat and firm treat ready to eat. Packed with flavor like no other bean out there. Few of us recognize the skill and labor necessary to produce this humble, trusty device, the toilet. It is both part engineering and art. But in order for one of these to be sold to you, it must comply and meet some pretty strict standards in terms of the amount of water it uses. And that is an ongoing challenge. How is it that pure physics can wash away a bowl full of waste?
To find the very first toilets, you'd have to go back thousands and thousands of years. In fact, archaeologists uncovered sitting-type toilets in Egypt dating back to 2100 BC. But it wasn't until 1775 that the first patent was issued for a flushing toilet to Alexander Cummings. As you can tell by the fully stocked shelves here at the Kohler Company, we've come a long way from, well, water closets and chamber pots.
It's a fast-paced process that the folks here at Kohler have perfected. Here at the plant in, where else, Kohler, Wisconsin, they crank out thousands of toilets. Few people would ever see it this way, but when you visit the John, you're actually sitting on a finely honed sculpture, one that's made of 4 different materials. The main ingredient is called slip. It's a combination of clays and minerals, and when it undergoes intense heat, slip becomes ceramic and gives a toilet its solid structure.
Just on a little bike ride down here in the bowels of Kohler, the basement. It's down here where they pump all that slip and they test it. They test it some 35 times a day to make sure the recipe for that slip is just the way they want it. Nice and perfect. So what's in this stuff anyway? I mean, I know it's kind of a clay-like liquid substance, but what are the ingredients?
Clay. Actually, there are 4 key ingredients.
Slip is made up of 2 different types of clay. Flint, a type of quartz, and feldspar, a substance that helps fuse the materials together in the kiln's intense heat.
That's what helps make toilets so rock solid. Finally, water is added to the mix. They age the slip for 3 days, then they pour the whole mixture into toilet molds. This is where Kohler makes all of its molds.
They don't stop.
The workers here are pouring plaster, and the pace is frenetic.
You want it? Yeah, sure. Follow me and I'll
Okay. So this is coming out of here. This is coming out of here at about 12 gallons per minute.
It's like plaster. A fire hose of plaster.
You got to work fast. Plaster.
There we go. Okay, I got to go over. Whoa!
Lou's creating the various pieces that make up our master mold. Now that the plaster is hardened, the parts are assembled.
Lou, why use plaster? I mean, this is another delicate material here. Why not use metal or, you know, a steel mold or a plastic mold? That seems like it would just hold up better over the long run.
The slip dries not in air, it dries into the mold. In this case, plaster is absorbent like a sponge. The slip is going to dry right into the mold, into the plaster, and harden. They'll pour out the slip in the middle and leave a hollow shell of ceramic. You need an absorbent mold to make toilets.
So this is all about a game of drawing moisture out of the slip.
Our mold's ready to go, and there's only one thing left to do.
Time to make the toilet. Steve, I got the mold here. Let's pour a potty.
The slip, our stew of liquefied clay with minerals added, is pumped through pipes and into the molding area, and this is where the real technique comes in.
So you know this is full, obviously, when this funnel starts to back up. You know you've done it?
Right. It is. That's very...
And it's got... Oh, watch out. Okay. I've only been here 5 minutes, and I'm screwing up your toilets.
This is Steve Risch. He punches in at 5:30 a.m. and never stops moving. Steve's been at it for 20 years, hand-making toilets, sinks, and urinals.
So at any one time, you've got 4 or 5 processes going on at the same time. You've got toilets being poured, you've got lids being made, you've got these stands being made, you've got drainage happening. You're like a chef making a 5-course meal here, except it's a toilet.
Today, we're making a jet-assisted toilet. That's Kohler's answer to creating more efficient toilets. In 1994, Congress passed a law that requires toilets to use less water, no more than 1.6 gallons.
The way this toilet does it is by feeding most of the water from the tank through a jet, where it comes on a very high flow rate, picks up the waste, and blows it through this curvy tube known as the siphon. Now, as the water goes up and over the siphon and down the far end, the weight of that falling water and waste creates a partial vacuum at the top of the siphon that sucks everything else out of the bowl. But when the job is done here, the bowl is empty and everything is in your plumbing.
So that's where that hole is being made, right here.
That's the jet hole.
That's the jet hole. That's the most important jet, I think. The one that really just gives you the most bang for your buck, you know? The one that really shoots the water right down.
Yep, that pushes her out.
Pushes her out. And we all know what the her is.
Tell me about the temperature. You keep it, what, 85 in here at all times? What is it?
The ideal temperature is 80.
You're sweating all day long.
Oh, yeah.
It's hot.
If it would be cold in here, if that mold was cold, it wouldn't work. No, it wouldn't work.
Oh, it wouldn't work at all?
It wouldn't work.
The high temperature and low humidity speed the drying process. But there's a lot of work to be done before the clay shell gets too dry. When it dries out, it can crack. That's why Steve and Brian are working so fast. If the clay shell dries out and cracks while it's still inside the mold, it's a disaster.
Are these cracking because I'm here slowing the process down? Yes?
Yeah.
That was an affirmative?
Yep.
Great. I didn't know there was so much guilt involved in making toilets. Already starting to shrink away from the bowl here. So really we're racing against the clock here. You want me to clean these off or do anything?
Grab them yellow sponges.
Yep.
And then you can do, nope, the other ones.
A damp sponge can close up any hairline cracks that show up.
The toilets are drying. The toilets are drying, and that's a problem because when you have toilets drying, you have shrinkage. And when you have shrinkage, you have cracking. And I'll tell you what's really slowing the process down is having a TV crew here. It's your fault. It's your fault. Steve's gonna kill me. Hey, Steve? God, he's left me alone with the toilet. This is scary.
They start early around here at the Kohler plant in Wisconsin. 7 days a week, 365 days a year, they crank out toilets. So far, we've mixed up our batch of slip, which is essentially liquid clay, and we've poured that right into our mold. Now, after just 90 minutes, the slip is hard enough to begin removing the plaster mold. It's time to finally get a look at our handiwork.
I'm gonna lift it up, then you're gonna take it.
Just a little bit, and then I'll
Okay.
take it.
All right.
Okay? Hand it over. Hand it to me.
Got it. Oh, look at that. That is a toilet. I'm going to lift up, and then...
You're
like
handing
so.
it over. That
right.
way, the weight, when you're handing it, you're handing the weight across. Right? It keeps it off of
Yeah.
me, so that I got the weight more close to me.
You and I we could do Dancing with the Stars, or
Sure.
Dancing with the Non-Stars, or the Toilet Stars, or
Whatever.
something like that.
Sure.
Ready?
Yep.
Lift.
Yep.
And...
You're handing it over.
Oh,
Yep.
it's just like a tango, kind of. Just feel that synchronicity. I mean, obviously you'd use them right side up, but they look great.
Yep.
You can never stop being too careful, right? I mean, even at every stage, they're still soft, they're
Yep.
still very breakable.
Breakable, not really breakable here, but denting.
Our next step, turn these toilets into rock-hard ceramics. This is the dryer here at Kohler. The wear will spend 16 hours in this heated tunnel, 124 degrees, and its water content will drop from 15% to about 0.5%. If Kohler didn't lower the moisture content, the water would flash to steam. The toilet would explode like popcorn in the microwave oven. Just like 9th grade pottery class, it's time to put a glaze on our creation. So we move down the line to the glazing station. Now here, each piece is sprayed with a thin coat of glaze that's made up of glass-forming minerals and water. This is the last step before it goes into the kiln. Though the clay feels dry to the touch, it's still loaded with moisture, and it's pretty delicate.
I just broke a piece. These are very fragile. Is there a break it, you bought it policy here?
Yep. That's really my first break since I've been here.
Right after you said you're hired, did you notice that?
Then I broke the same.
Yep.
See, I already started to relax into my new job.
Bring it off the edge and put one hand under. Lay it down. Grab the back end.
So I'm pulling it forward, and then I'm going to tip it this way. So when I pull this forward...
What? Another... They make more.
I feel really bad about this. But I've seen how hard it is to make a toilet from beginning to end, and now I feel really, really bad. So basically, I just bought a toilet, too.
A sink, a toilet, I've nearly destroyed an entire bathroom.
Only break one toilet
And then
one
you're
day.
From here, everything rolls through a 380-foot-long kiln, and it is hot in there. The temperatures are more than 2,100 degrees Fahrenheit.
So it takes about 43 hours for the wear to get from one end of the kiln right here all the way down to the other end. Now, these kilns were built in 1928, and they've been running 24/7.
It's during this journey through the kiln that our slip turns into a ceramic and the glaze turns into glass. Here's what happens. The intense heat of the kiln causes atoms to share electrons, creating incredibly stiff and strong bonds that can't bend without breaking. That's when the toilet becomes a single solid, a ceramic. 2 days after these pieces were first poured, the makings of a bathroom emerged from the kiln.
Wow.
Glistening, piping hot, and ready to be tested.
Fresh from the oven, new urinals. Beautiful. Finished product. Here's our toilet. Glazed, fired, now practically glass. And hopefully not as breakable as the last one I touched.
It's back on the bike for the long trip to Kohler's equivalent of Area 51, the top secret testing zone.
Andy Weaverdink runs this laboratory for the most part, right, Andy? Mm-hmm. And behind us, 4 models of Kohler toilets where you're going to sort of put them through their paces, as it were. Now, what happens, Andy, when you start getting into other more bulky media, as you call it? Let's just call it what it is, a dookie. I mean, you get a big dookie in there.
Yep.
How do you simulate that?
I'll grab this stuff over here.
This is about as realistic as you get. Now, we should add, these are actual dried condoms filled with
soybean paste.
Soybean paste.
Right.
So this is as close to the real thing as you get, basically, in the lab. So we got a bucket of dookies. We're going to dump these in?
One at a time.
Okay, but total, how many would go into the bowl for the test?
20.
20?
Up to 20.
Up to 20.
Right.
Well, that was one hungry person. 14, 15. We're getting into gas station bathroom territory here. 18, that's Bigfoot. 20. That's who did this in here. By any standard, that's pretty excessive.
That's very excessive.
Well, I handled that like a breeze.
I couldn't resist the urge to really challenge my toilet just one more time.
So let's just say a 4-year-old playing where they shouldn't be takes this guy. What's the word?
Water weenies?
Water weenies. That's what I was looking for. This is a real test. I mean, there is in there a goldfish and 4 water weenies. Should we take bets from the crew? Mark says yes. Steve? George?
The duck's gonna kill it.
No, Faith?
No chance.
No chance?
No.
I'm gonna say yes. Oh! George and Faith, walk home. Thank you for playing today on What's That Flush? That was impressive.
Pretty cool, yeah.
That was impressive.
Probably could have done more.
You know, already I bet Hollywood is scrambling to just make what I just did a game show. Like that?
Yep. Push it right in.
And any toilet that can handle a load like that is clearly ready for prime time.
Say bye.
There it goes. It's kind of sad to see them leave. They grow up so fast.